Okay, folks, so as is typical, in the last section we learned sort of a general strategy for solving these systems of equations, systems of ODEs, in which we look for the eigenvalues and the eigenvectors, and usually we have e to the eigenvalue of t times its corresponding eigenvector, and that combined with the other eigenvalue eigenvector pairs gives us a general solution. What we're now going to look at then is a number of special cases for this procedure, and the first one we should tackle is what happens if 0 is an eigenvalue. So let's go ahead and do the work to find the eigenvalues and eigenvectors for this system just as a review. So for our matrix A here, well, we've got our matrix A stated up here, so let's go ahead and compute its eigenvalues. We'll do so by looking at the determinant of this new matrix, which in this case would be the determinant of 4 minus lambda to 2 minus 1 minus lambda. And if we compute that determinant, let's see here, that gives us lambda squared. That gives us plus 4, so plus 5 lambda, and then we have plus 4 there. That's for the first expression, minus 2 times 2 for the second. And so we end up with lambda squared plus 5 lambda, and if we set this characteristic equation equal to 0 to find the roots of it, we end up with lambda times lambda plus 5, so we end up with lambda equals 0 and lambda equals negative 5. So it's precisely what happens when we have an eigenvalue of 0. That's what we want to discover in this example here. So let's go ahead and find the corresponding eigenvectors for these. So let's pick lambda equals 0, find its eigenvector. So if we pick lambda is equal to 0, we return to this equation here, a minus lambda I times v is equal to the 0 vector. And so we would have, in this case, we're picking 0, so we would just have the original matrix, minus 4, 2, 2, minus 1 times v1, v2 needs to equal 0, 0. Folks, if you're confused by that, just go back to this matrix here. It would be minus 4, 2, 2, minus 1, and we're subtracting from that 0 times the identity matrix. So that 0, when I distribute it to all of the entries of the identity matrix, makes all the ones that already had 1s in them 0, and all the others remain at 0. And so we're simply taking matrix A and subtracting the 0 matrix from it. So that's why we end up with just the matrix A when our eigenvalue is 0. So let's go ahead now and solve this system of equations. So if we get a 1 in the first, well, let's adjoin it, so we get minus 4, 2, 2, minus 1, adjoined with 0, 0. Getting a 1 in the first pivot position by dividing by negative 4 gives us 0, or excuse me, gives us 1, minus 1/2, 0, 2, minus 1, 0. And then multiplying the first row by negative 1 and adding down gives us 1, minus 1/2, 0, multiplying by that will give us 0. That'll give us a positive 1, so that gives us 0. And yep, that's exactly what we were expecting to get when we found this, when we solved the system, because this was a distinct eigenvalue with no repetition of roots. Okay, so it looks to me that v2 is free, and that v1 is equal to 1/2 v2. So it seems to me it makes sense to pick v2 equal to 2, and then v1 would equal 1, and so then here we have our, then here we would have our eigenvector for the eigenvalue 0. So then we can take the other eigenvalue, and we'll pick for lambda equals negative 5. In this case we would have, now careful here, we have minus a minus 5, so we end up with 1, 2, 2, and 4 for a minus lambda I times v1, v2 needs to equal 0, 0. Okay, folks, again, I'm just returning to this equation right here. Let me put it up here. A minus lambda I times vector v needs to equal the 0 vector. And here I'm using negative 5 as our lambda value and the same original matrix A. So if we go through and solve this system, let's see here, we get 1, 2 adjoined with 0, 2, 4 adjoined with 0, and we do the row reduction here by multiplying by -2 and adding down, and sort of as expected, this is what we end up with. And so we get that V2 is free, and that V1 is equal to -2 V2. So let's pick V2 equals 1, which would mean that V1 would equal -2, and so our eigenvector associated with the eigenvalue lambda equals -5 is this eigenvector here. So what's not really new is how do we give the solution to this. So our solution is C1 e to the lambda equals 0, so 0 times t times its eigenvector, which we said was 1, 2, plus C2 e to the second lambda, which was -5 t, times its eigenvector, which we picked -2, 1, or one of its eigenvectors, I guess I should say. And since we have e to the 0t, that's just 1, so we really just end up with C1, 1, 2, plus C2 e to the -5t, -2, 1. So in some ways, coming up with that solution was really just a refresher in what we did in class last time in solving these systems. The real question that's going to be different in this case is how do we go about sketching the phase portrait for this system. So as before, we made our coordinate system, and be careful here, folks. This coordinate system, or this phase portrait, time doesn't show up on one of the axes here. Instead, we've got x1 of t, and we've got x2 of t, the two solutions that will simultaneously solve this matrix equation, and we'll see how that adjusts. So what did we do before? Well, we went ahead and we plotted our eigenvectors. So in fact, let's go ahead and take off with this one here, because there's nothing different here, where we're going to plot the vector -2, 1, and there's that vector. And then the same work holds as before. It's got a negative eigenvalue, so I'm going to put a directional arrow pointing inwards like this, and we can go ahead and extend this eigenvector span, or if you like, the eigenspace through this plane with the arrows pointing inwards because of that negative eigenvalue. That is, if we only had this expression right here, because this C1 happened to be 0, then we would expect this to tend towards 0 as t gets large because of that negative eigenvalue. Okay, so now let's go ahead and plot the other eigenvector, which is the vector 1, 2. So let's see here, there's 1, 2. So there's that eigenvector there, and I'm going to go ahead and plot it on here. Okay. And there's no real way I can assign a direction to it. How come? Well, because my lambda here is 0. But let's go ahead and extend the eigenspace through the plane. And then what do we find? Well, in all cases, regardless of our choice of C1, this is just going to have sort of an initial vector, and the only thing that's going to drive how this changes is the second term in this equation. Okay. And what we saw before with a lot of our other phase portraits, for example, when we looked at, say, this one right here, we had maybe phase portraits that looked like this, and like this, and like this, and like this. Something where as time progressed, we became parallel to the dominant eigenvalue. So we became parallel to the eigenvector associated with the dominant eigenvalue. Well, in this case, we only have one eigenvalue that will dictate what this solution looks like. And so let's say we started out in this position here. Well, what are we going to do? Let me use a different color here. What are we going to do here? Well, we're simply going to begin moving parallel to the eigenvector that shows up in this the only non-zero eigenvector eigenvalue in this expression. Okay? So these will be what all of our solution curves look like in this case. Now, in this example, notice that because we had a negative eigenvalue to begin with, as time progresses, that component should go to 0. this entire component should go to 0, and we'd only be left with whatever C1 times this eigenvector is. And so as time goes to infinity, we land at somewhere along this this eigenspace line right here. So keep that in mind, because when you do the next example on your own, you're going to have a positive eigenvalue, and I want you to think about which way the arrows will go on that. You'll have a similar picture as this one, but you'll have a positive eigenvalue. All right. That's all I've got for this. Let me know if you have any questions.